Should I start or wait a bit more?
Yes, sir, I think we will start so that we finish on time.
Okay. All right. So let's continue. So I've introduced the first steps of the replica method, meaning the replica trick, which is a way to convert the problem of computing the log moment of a random variable into the computations of usual moments, with a catch is that I will need to make sense of these moments when k goes to 0. Okay, so this is something to keep in mind. Okay, so let's then start the computation. So using the replica trick, now the goal is to compute expectation of z to the k. Okay, and so even if later I will need to take k going to 0, I will assume at the moment that k is an integer. Okay, and we are going to obtain a formula for this. So again, I'm sorry, could I ask some of you to show their face? I see always the same person, very Miss Madame Professor Kagar. Nice to meet you. If some students could show their face, it would be great, please, because it's really difficult to talk in front of a black screen all day. I would like to see that some people participate. Really, this is important. Okay, I cannot force you, but I find a bit strange this experience of not being present in any way. Anyway, okay, let's continue.
Candidates again requested to switch on the cameras. All the candidates are once again requested to kindly switch on the camera, and please respond to Professor John Barbier.
Thank you very much. So, yes, it's nice to see that people are actually there. So, we're computing this moment, and the key point is that we're going to assume that it's a standard moment, right? So k is an integer number, and later on, so we're going to obtain a formula under this assumption, and we're going to then make the assumption that the formula we obtain is still valid, remains valid when we extend it to real values of k, in particular close to 0. So this will be an analytic continuation from the set of integers to reals, under the assumption that the resulting formula remains true when extending to real k. Okay? So that's the main idea. So now that we have a integer k, we can write down this expectation of z to the k in a meaningful way. So what is it? It is the expectation of the integral, so the normalization of the posterior distribution, which is dx px of x, and I will use this notation now to mean. Okay, expectation of some ij of yij square root lambda over n, xi xj minus lambda over 2n xi xj squared. Okay? Perfect. And this to the k. So if I take an integral to the k, this is the same, of course, as just introducing k dummy variable, integration variables. Same thing with xa. Okay? So what I've just done is called replicating, and that's why the method is called the replica method, because you see what I have now, this z to the k there is just the partition function associated with k replicas of my original system. Okay? These replicas, they have something in common in the sense that all these systems, so let me write explicitly, otherwise xia xja. You see all these replicas, which are indexed by these variables xa's here, I call that a replica. They share this y. They all have in common the same disorder, the data in this context. Okay. So now the goal is to compute the average over over this y. Okay. And now this is possible. This is possible because I don't have the log anymore, which was stuck there. So now this expectation can be pushed inside the integral there in front of the exponential. And you see that this y, what is it? It is a Gaussian variable whose mean is related to the hidden signal x star, and the variance is 1. Okay? So I need to compute with respect to a Gaussian distribution the average of an exponential where I have my Gaussian appearing here times a term. So this is computable. This is possible. Okay? So I'm now moving my average over y here, and I can rewrite this as product over I less than j of expectation of yij of this exponential. Okay? So remember that yij, it's a random variable, which is a Gaussian distribution with mean square root lambda over n xi star xj star and variance 1. Okay? So I have something of the form expectation with respect to, yeah, I mean, I don't need to rewrite. I have this term here to compute. This is just a Gaussian integral. Okay? So it's explicit. So you can do this Gaussian integration, and what you obtain with respect to yij, what you obtain, let me write it. So using, let me write explicitly the formula that I'm going to use. that you should all know in the integral with respect to, let's say, a z, a Gaussian z exponential minus az squared plus bz is square root of pi over a exponential b squared over 4a. So this is the Gaussian integral formula that you need. And if you use this for every ij here, what do you get? You get there remains an expectation with respect to x star that we haven't integrated. Integral of product over a equal to 1, sorry, a equal to 1, 1 to k. A is called the replica index because it's indexing my replicas of my system, just my copies of the system. Dxa, where really xa is a vector, px xa, exponential sum I less than j of lambda over n xia xja xi star xj plus lambda over 2n sum over, I will write the 10 here. Yes, excuse me, I'm missing. Sum of a equal to 1 to k. Sum of a different than b from 1 to k of xa xi b xja xjb. Okay, so you see this term, so this term was already there. It corresponds to the mean of yij acting, multiplying this thing. And the integration with respect to the noise, or equivalently if you integrate directly with respect to this, is the same. You obtain this, so you have this interaction between all the replicas and the signal, the ground truth, x star. And now you have this term, which is quadratic. And you see this quadratic term, it's quadratic in this sum. It's essentially a sum to the square, okay? It comes from, you see, the fact that when you do a Gaussian integration like this, the noise, the Zij that was acting on this for every A, here I'm again missing something, I'm sorry. I can rewrite like this. This Gaussian is multiplied by this whole sum. So when you take this sum to the square, this is how you construct this kind of terms, okay? So what do we get? So really here I've done nothing, it's just a Gaussian integral. You can just do the exercise using this formula and using this distribution for y. There is nothing fancy. But we have done something conceptually important. We started from this partition function, which represents, sorry, yes, here. We started from this partition function, which is just z to the k. It represents the partition function of k copies of your system. which conditionally on the data, on the disorder, are independent. So what they have in common is this disorder here, but if you condition on it, you say it is fixed. This just corresponds to k independent system. It's just an integral to the power k. Okay. But now when we integrate out the noise, or equivalently the data, conditional on x star, we couple these systems, these replicas. So what we do is that we start from k independent replicas sharing the same disorder, and by integrating out the disorder, we couple these replicas. But what we gain is that there is no more disorder, there is no more noise. Okay, you see now this system here, this integral here, there is no more presence of the noise matrix Zij, which was the problem in the sense that it prevented us to identify an order parameter like we did for the Ising model and to integrate directly by Laplace. Okay, so there is no more noise, which is a good thing. So now, hopefully, there's a chance to identify order parameters like we did for the Ising model. And indeed, we will be able to do so. Okay, so these are the next steps. Okay, so the first thing I'm going to do is to make this expression a bit simpler by simply denoting x star, which represents the hidden signal, like another replica. It will be x0, okay? And you see that this expectation with respect to x star is of the same form as expectation with respect to the prior of the other replicas, because we are in the Bayesian optimal setting. So the prior used to generate the signal is the same that the statistician is using when writing down the posterior distribution, and so it's the same as what appears here. Okay? So if we simply change notation and call x star x0, it becomes like another replica. It's just another replica playing a symmetric role with the others. So all this integral simply becomes an integration from a equal to 0 now, which includes this expectation, to k of dxa px xa. Okay, and you see that this term is the interaction between x0 and the other x's. So I can absorb this term into this sum. And so this sum now will start from 0 to k instead of 1. Okay? So all this exponential becomes very symmetric, very simple. From a different than b, from 0 to k now, of sum of I different than j of xai, xib, xja, xjb. Okay? Just using this notation. So I've done nothing. I just changed notation. And you see, now I'm finally in a position to use the exact same trick as in the Ising model. Because what I recognize now is something that looks very much like a square of an order parameter. You see, this sum over a different than b is like a square up to a diagonal term a equal b that I can add and remove to complete the square. But it's really like in the Ising model. I have a kind of magnetization that appears again. And this magnetization is actually the overlap that I discussed yesterday. So let's see that. So let's complete the square first. Yes, so you see here I'm putting a 4 instead of a 2 because this sum over I less than j can be written as a sum over I different than j with a 1/2. Okay? Perfect. And this is sum. So first I want, there are two types of squares here that appear, by the way. There is a double sum here over the indices of my vectors, and there is a double sum here over the replicas. So we are going to treat these two squares one after the other. So we're starting to treat the square due to this double sum here. Okay? So let's do it. So first I leave this sum there untouched. And this becomes a sum over I from 1 to n of xia xib to the square. And of course here there were terms that were not, there are terms that are counted here that are not present here when I equal j. So I need to remove this I equal j term, because they were not present in the original sum. Okay, so again I've done nothing. I've just recognized a sum to the square, which I wrote explicitly. Okay. Perfect. So what do you recognize here? So first, is there a question, or at the moment the manipulations are clear? I will assume that if you don't stop me, I can continue, but there is really nothing fancy at the moment. These are just basic algebraic manipulations. Okay. So now that I have manipulated this replicated partition function, this z to the k, which I have averaged with respect to the disorder, the noise and the signal, I am recognizing an order parameter. You see here, this quantity looks like it's an angle. It's an overlap. So it's the angle between the replica XA and the replica XB. So it tells you how much these two replicas, which you should think as, so the physical meaning is that replicas are just conditionally independent samples from the posterior distribution, from the same posterior. So they share the same disorder. You remember that we started from z to the k, and this is the law of just k independent this is, sorry, the normalization constant of the posterior distribution of k independent samples from the posterior. So these replicas, really, their meaning is just different samples from the posterior, from the same law. Okay? So this is the angle between two different samples from the posterior distribution. So if this is 0, it means that each time you sample the posterior distribution, you get a new high-dimensional vector that has nothing to do with the others, with the other samples. So it means somehow probably that the posterior distribution does not contain any information about the signal. If you sample each time orthogonal vectors, they have nothing in common. It's probably that you are in a region, there is no enough information in the data to recover the signal. If, however, when you sample twice the posterior distribution, these two vectors that you get look alike, they have an inner product which is non-zero in the large size limit, it means so they are correlated, it means that probably the postal distribution does contain information about the signal. And this common direction, so that they are pointing at, is the signal, actually. Okay? So let's introduce this order parameter. Let me give it a name. So I will call QAB, which is a function of XA and XB, simply 1 over n XA transpose XB. Okay, so this is the overlap between replicas A and replica B. Which again, replica means sample from the posterior. So you see, it's like a magnetization, but it's like in the SK model. You are comparing samples from the measure, and you're checking whether they have something in common. Okay. So it's a more subtle order parameter than the magnetization, because in order to compute it, you see you need to sample twice the distribution. You need to obtain 2 independent samples. While the magnetization in the Ising model, you just need to get 1. You just sample it once, you compute the mean, and this is a magnetization, and it tells you whether you are ferromagnetic, paramagnetic. Here when you have disorder, in spin glasses or in inference problem where you have data which plays the role of disorder, the only way to make appear the order parameter is to replicate, and so the order parameter are functions of more than 1 replica, in this case 2. So it's a more subtle quantity. It only makes sense, the order parameter appears by comparison between samples. Okay? Perfect. So using this order parameter, now I recognize that my replicated partition function, the average of my replicated partition function, is equal to integral over all my replicas from 0 to k of dxa px xa of exponential lambda over 4n, sum of a different than b of q ab to the square. Okay. Minus lambda over 4n sum a different than b sum I of xia xib to the square. Now I will make a simplification. I will assume that this term here does not matter, that I can simply remove it. Why is that correct? So again, the replica method is not a mathematically rigorous method. You allow yourself simplification heuristics, then you get the results, and then you can prove a posteriori that is the case. I claim that this simplification is exactly correct in the large n limit. Why? Because you see this term, excuse me, here there is no more n. It's the opposite, the n is there at the numerator. You see, I define the overlap with the 1 over n. Here I have a 1 over n, but here I have a square. So I put a 1 over n there, and therefore I need to remultiply by n. This is the correct term corresponding to that one. And the other term corresponding to that one is here. But I claim this second one can be forgotten, because you see, this term here will scale, will be of order n, because this quantity, this overlap, should be of order 1. It's the inner product between vectors, so it can be 0, but typically, if there is information in the data, this order parameter will be of order 1. So we expect this term to be of order n. Instead, this term is of order 1. You see that you have a sum over n terms here, and there is a 1 over n here. And of course, these variables, they are of order 1. So the prior, let's say they are plus or minus 1. Let's say they are binary variables, like in the SK model. So these are plus or minus 1s. This is of order 1, all this. It's an empirical average of these squares. So this order 1 quantity can be dropped in front of this order n quantity. What dominates this integral is 1. So we are going to simply forget this term. You can show very easily, rigorously, that you can drop it. This is not a problem. Okay? Perfect. So let's continue. So you see now we are in the very same position as like when in the Ising model we had something like we had decomposed what we had recognized that we could write the partition function as a sum over sigma of exponential of a function of the magnetization. And the trick was to say, let me decompose this sum as a sum over the magnetization itself. And then I need to sum over all configurations that have this magnetization. And this was the entropy contribution. Here we need to do the same trick. Now we have recognized that for this replicated system, the energy, which is this part here, is a function of a macroscopic quantity, so a kind of summary statistic, which is this order parameter, this overlap. So we need to decompose this integral, which is the sum in the Ising model there, into an integral over the values that the order parameter can take times the degeneracy of these values. So how many microscopic configurations, microstates in the physics language, simply how many configurations of the x's of the replicas are in agreement with a given value of the overlap, like here. How many configurations of the spins are in agreement with a given value of the magnetization. The magnetization is here the overlap. Okay? Perfect. So the way to do that concretely will be simply to introduce a very almost trivial identity. So let's write this entropy. So right, so the entropy was this term in the Ising model. The equivalent here, so let me define exponential of gamma of Q. So where Q is the matrix B's. As an integration over my replicas times delta functions that enforce this constraint. So you see, what is this? It's an integral that is counting the volume. This is the volume of configurations. Okay, this is the integration over my configuration space. And I'm integrating only the configurations such that their overlap between xa and xb is equal to some value that I fix. Okay, so I'm restricting, it's like I'm cutting the space of configurations into subparts that we call the macro states. And the macro states are defined by the value of the overlap. Okay, so I'm enforcing the angle between different replicas to be something that I call little QAB. And I look at what's the volume of configurations that verify these constraints. Okay, so this is the entropy. It's the same role as this. Here I was counting the number of configurations with a given magnetization. It's the same thing. Okay, except that now we're working a bit more generically with possibly continuous variables. I'm computing a volume and not just a number. Okay? Perfect. So now I'm going to introduce this entropy in the previous term, in the previous integral that we have here, by using the trivial identity that 1 is equal to the integral with respect to all choices of this matrix Q. So Q really is a matrix of size, so this is a matrix of size k plus 1 times k plus 1, the total number of replicas, exponential, okay, and this is indeed 1, because if you integrate with respect to all possible choices of this matrix, this delta function, this gives 1, and then the remaining integral with respect to all the configurations is 1, because this is normalized. These are well normalized probability measures. So the total volume is 1. If you want the total volume of configurations weighted like this is 1. It's normalized. So I can plug this identity just here. I can put a 1 there without changing this integral, right? So I can do that. Integral product over A goes from 0 to K. Exponential lambda n over 4. Sum A different than B and QAB squared. And then I have an integral with respect to this matrices Q of exponential omega Q, which is all this. Sorry, if I integrate this with respect to 1, so I missed that this part is what I wrote there already. Product over A different than B of delta QAB minus QAB, where again remember that when I use a capital Q here, this is really a function of XAXB, okay? While this little q is just a number. Okay, I hope you're still following. I've just introduced, I took the previous integral that I multiplied by 1. I multiplied the integrand by 1. But this 1, I wrote it in a smart way. This 1 is the integral over all possible values of my order parameter of the entropy of this order parameter. Okay? I'm summing over all the space of configurations cut into parts, and the total volume is 1 because I'm working with a normalized volume of probability distributions. Okay. Perfect. So now I'm going to use a trick which is probably one of the most important trick in theoretical physics but not only, it's used absolutely everywhere. Is the fact that these deltas, they are enforcing these constraints that this function of xa and xb should be equal to this number little qab. But this is not very practical to work with. I mean, the only thing I can do if I keep the delta written in this form is to integrate again q and just come back in the computation. I would undo what I've just done. So somehow we need to write this in another form, okay, that become useful. And the trick in physics, and this is the basic trick in spin glasses, in quantum field theory, in field theory in general, it's used everywhere, is the fact that you can write the delta function using what we call its Fourier form, okay? So in particular, what you know is that 1 is equal to the integral with respect to x of delta x by definition of the delta function. But this delta x, you can rewrite it in another way. You can rewrite it like this. 1 over 2 pi integral with respect to x integral with respect to the imaginary axis. So you're integrating on the imaginary axis a kind of auxiliary variable. It's called the Fourier conjugate, exponential x hat. Yeah, there is a typo in the notes. I will correct it right now. I will correct it after. X, okay, or if you want, if there is a minus a there, it would be x minus a. Maybe not a, because this is the symbol we use for replica. Let's say x bar. So this is the Fourier representation of the delta function. So you see that it's indeed true, because if x is different than x bar, you are integrating this x hat, which once again, I've not done typos. Yes, so this is a complex exponential. This x hat is a complex number. So I'm integrating an oscillating function, and so this integral will be 0 if this is non-zero. So if x different than x bar. Instead, it will be 1, and this is the normalization associated with this integral, only if x equal x bar, which is the same property as the delta function. So it's just a way to represent the delta function using a Fourier representation. Okay? So it's an important trick, because doing so, this delta function will be written in exponential form like this. So we will have a big exponential that we can then continue to manipulate. So let me use this. So I plug this representation here in our previous expression. And so what we get is the following. 1 over 2 pi. So these are coming from the delta functions. I have also an integral with respect to q, and which is a matrix, and q hat. which is a matrix. So the Q hat is what I call X hat there. It's the Fourier conjugate associated with the Q's. And so I need one Q hat AB. I need a Q hat AB for every delta function like this. Okay, so I have a matrix of Q hats at the end of exponential sum of A different than B, 0k of Q hat AB, sum of I equal 1 to n of xi A xi B minus n QAB plus lambda n over 4 QAB squared. This is indeed correct. You see that this exponential is like this. It's my delta function. So, and the delta, the constraint that was enforcing is that little QAB equal to capital QAB, where the definition of capital QAB is just 1 over n sum of XIA, XIB. So this is indeed enforcing this. I've multiplied both by little n, so I have that this sum should be equal to n times QAB. Perfect. So these are my delta functions. And here you should keep in mind, in the back of your mind, even if I think, that this Q hat could be complex numbers. Okay? So we'll comment more on this at the end, but at the end it will not matter complex or real, because they, even if a priori there are there are complex numbers, the way we're going to integrate the final formula will be by saddle point. And so we will essentially find a contour in the complex plane for Q and Q hat, and we will realize that the saddle point is dominated by real value. So at the end, in reality, this Q hat will be reals. Okay, and this is a consequence of saddle point estimations. I cannot do a course on saddle point integration, but if you've never seen what it means, I recommend that you take a look. It's a very important mathematical tool. But just keep in mind that even if it is true that here the X hat is integrated over the imaginary axis, I will at the end deform this contour and just select one point in the complex plane, which will be, and this saddle point will end up being on the real axis. So these numbers will not be complex. So that's why I'm kind of dropping right away this notation. But okay. Perfect. So, and you see here now this term, the energy, I've replaced the capital Q, which is the function of the replica's x's, by the little q, because of these delta constraints, the capital Q and little q take the same value. This is what I'm enforcing. So I can replace this by little q. So this is my QAB squared here. Okay? Perfect. So you may wonder, why do we have to go through these delta functions with this Fourier representation, all that? It seems complicated, while for the Ising model it was very simple. For the Ising model, right, I could directly compute the entropy. Yes, this is true, but this is a much simpler problem. So the computing how many sequences of binary variables have a certain mean is a very simple problem. If instead you ask how many, if you ask what is the volume of real vectors weighted by these probability measures such that their angle is little q, and these angles can be different for two different vectors, so you are kind of forcing a set of vectors to have specific angles between them, and you want to know what's the volume of configurations in agreement with these angles. This is a much more complicated problem. You cannot compute it directly. So that's why you need these tricks. Okay? Perfect. So, where are we? We are there, and so look, we have done something very important now. We have linearized in the space of what in physics you would call the real space, which is the space of components of this vector. What do I mean by this? If we look at the expression before some manipulations, which is here. So this is the replicated partition function before the manipulations we've done by identifying this square and so the overlap. Here we have a sum over I different than j, and these terms are dependent on both I and j indices. Okay? So you have, this is a coupling in real space. This I and j represent in physics the real space, the real dimensions of the problem. While you have another dimension now, which is this replica space, this replica index. You have multiple copies. But we have this kind of couplings in ij, and what we've done by identifying the order parameter and simplifying is to obtain an expression where you have no more interactions between I different than j. You see, now we have taken care by identifying the order parameter of these couplings, and now we just have a sum over I, right? So the trick is that, of course, the coupling is kind of hidden there, because by these delta functions, you could replace again this by the capital Q squared, and if you expand the capital Q squared, you go back to a sum of I different than j. But here, because of this delta constraint, we could replace this by the single number QAB, and the only place where variables appear is this one, and this is linear in I. Okay? So by introducing this delta function through the identification of the order parameter, we could linearize this whole exponent in the index I. Okay? Which is key. So it's a first level of decoupling. Okay? Perfect. And the point is that now we can simplify the integral, because this, concretely, this means what? This means the product over I equal 1 to n of dxia pxxai. So you see that I can also I can write all this as this constant, it doesn't matter, integral of product over I equal 1 to n. Now everything is factorized in I. And I will put this integral over q and q hat there. So you see, this n, I can think of it as a sum over I of this quantity. So if you want, I can put this sum over I there, doesn't change anything. And basically, this sum over I is a product of exponentials over I. This is also a product, this is also a factorized term. So everything is factorized in I. So I can put this product over I outside of the integral. Okay. Minus QAB. And this also, this n, you can interpret it as lambda over 4 sum over I from 1 to n of this constant. It's just n times the same constant. Plus lambda over 4 QAB squared. And all this integral is to the power n. I have factorized my integral with respect to the vector indices that I call the real space. Okay. This is fully factorized over I now. Sorry, excuse me. Not. It's like this. Excuse me. When you do computations live, of course, you make mistakes. This is the product of this integral over I, but you see that this integral is just n times the same. You see, this is a dummy variable. This xi is just a dummy variable that I'm integrating over. So the integral for I equal 1 or 2 is the same. This is just an integration variable. So I can get rid of this product and just put a power n there. Okay? All right. So there are a few more steps. It's been an hour that I'm talking. We can finish the computation at the next lecture, but we're very close now. We've done 2/3 of the effort. So, okay, I will summarize next time again what we've done, but conceptually what we've done is we started from the system, we have replicated, we just took the same integral k times, we integrate the noise that these integrals have in common, that is really the noise in the problem, the zij's, and we went from independent replicas to coupled replicas, but without noise anymore, which are non-disordered, if you want. And then we identified the order parameter. We've seen that now we are in the same position as the Ising model, where we can recognize that the energy is simply a function of an order parameter, which is not anymore just the magnetization, it's the overlap, which is the angle between these vectors. And by introducing this overlap, we could move forward by introducing its entropy. So we decomposed the integral, this replicated partition function, into an integration over the possible values of this overlap and an integration over the configurations in agreement with that value. This is the entropy. And the energy is just a function of this order parameter QA. Okay, and by doing so, we realized that we somehow succeeded decoupling the problem in the indices I. The exponent became linear in I, which allows us to write down a single integral to the power n. You see that now it's not anymore, this is not anymore a high-dimensional integral. This is a one-dimensional integral. We went from an n-dimensional integral with n going to infinity, which you have no way to compute, into a one-dimensional integral. So of course we have to integrate this also afterwards, but these are also scalars. They do not depend on n. There are few variables. So the high dimensionality has disappeared. This is just a one-dimensional integral to the power n. So now it's something you can compute. Okay? All right.
Okay, sir. So after 1 hour, are we joining or after 2 hours?
In 1 hour, I guess. Yeah.
Okay. Okay. So thank you, sir. So we will be joining back after 1 hour at 3:30 as per Indian time.
Okay. See you later.
Okay, thank you. I thank everyone for patient hearing. Thank you, John Barbier, sir, for your kind, fruitful insights. Thank you.